you know what you did to cause that? Back on that.
Okay. Yeah, nicely. Yeah. Okay. Hello? Good. Good afternoon. I'm Matthew Shuchman. I'm the founder of WarDrivingWorld.com, and I'm here to talk to you about WarDriving hardware and how to build some if you want to WarDrive. Firstly, can I ask the question, how many of you have ever gone WarDriving? Can you raise your hands? Hey! Okay. So the rest of you are interested in WarDriving, and the ones who have already WarDriven want to do some new things. So great. What? Mike? Better? Okay, that's better? Okay, sorry. Yeah, well, I'll be all right. Okay. What is WarDriving? To start off, if those of you who haven't done it, WarDriving is the sport. The name was coined by Peter Shipley. The act of driving around and looking with a laptop computer and locating access points for Wi-Fi networks. You don't necessarily need an antenna. You can use an internal Wi-Fi card on a laptop, but you can only go so far with that. There are a variety of pieces of software that have been shared by their authors or in the public domain, including packages like Maurice Milner's NetStumbler, which allow you to record the access points that you find and record some information about them. And there are also packages like Kismet and that variety, which scrap Wi-Fi packets, and then to dissect them a bit and do little bits of surgery on them. First question, is it legal to WarDrive? Okay. Doonesbury slide.
That's where we're from, you know.
Is it legal to WarDrive? It's a good question, and it's one that I'm going to be covering more in tomorrow afternoon. There'll be a session on the legal and ethical aspects of WarDriving. I'm the chair on that, and Frank Thornton will be there, Robert Hale, and Renderman, and the four of us will be having a panel discussion on some of the current legal issues and some of the ethical issues in terms of WarDriving. So I hope you can join us there. Yes. And they've moved the time a few times, but I think it's at 1 p.m. tomorrow. I guess they'll let me know tomorrow, but look forward to seeing you there. Okay. Simply put, the construction of WarDriving tools is legal. And WarDriving is legal as long as you don't try to access a Wi-Fi signal that you don't have permission to access. Simply detecting the signal, so far, all of the cases that have come forward have shown that at least accessing the signal is a problem, potentially. But simply detecting the signal is not. The problem comes in when you have a typical case of, let's say at home, I have a Linksys router. I pull the Linksys router out of the box. I configure some security there. And what do I use for an SSID? That is the name on the router? Default. Okay? This seems unique. I now have my Windows XP laptop configured that when it sees default, it knows it's my home network and it links to it. Well, I drive around town. You're going to find a lot of Linksys routers configured with the name of default. And what does Windows do? And when linked up with Linksys, it simply goes and connects to the network, and it thinks it's yours. So, actively, you haven't done anything. But the software and the hardware, it's have combined, the software and the firmware have combined basically to allow you to have access to that network. So that's when the question becomes a little tricky. So we'll be discussing that more tomorrow. Yes, next slide. No, hold on the slide. Thank you. The original WarDrivers were those IT folks who were asked to perform site surveys for the design of Wi-Fi systems. Their purpose was to see where the signal was emanating from, where it was strong, where it was weak, and where it needed to be changed. This is certainly a legal form of WarDriving because they're working with signals that they've been contracted to work with, or they're working with signals in their own company. Yes, there have been a few arrests of people for WarDriving. Don't be scared. So far, there have been no cases of anyone arrested for WarDriving that wasn't associated with some other nefarious activity. That is, they committed some other crime. Most of us, I think, would agree if you're using... I'll take questions later. Thank you. Most of us would agree that if you're dropping in on somebody else's Wi-Fi signal and sending out child pornography as spam, that that's a crime, and that has nothing to do with the fact that they happen to be WarDriving while doing it. Or going up online on Wi-Fi and stealing people's credit card numbers that are coming across from a retail store. The crime really is not the WarDriving. The crime was stealing the credit card numbers. So far, there have really been no yet recorded arrests for WarDriving. So, to start doing WarDriving and performing Wi-Fi site surveys, what do you need? As I said, if you already have a laptop with built-in Wi-Fi, that's all you need. You can drive around with that and a piece of software like NetStumbler, and you can detect networks. The first time I went WarDriving, I lived in South Florida. I drove in a 4-mile square, 4 miles on each side around my house on major roads. I detected 83 access points. Approximately 15% had some form of protection. All of the others were naked. The SSIDs, that is the name given to the networks that were naked, included a local hospital, 2 law firms, one of which was named Law Firm, and the other one which was named by the name of the law firm, so certainly they weren't trying to hide, and 1 bank and 1 local city agency. Obviously, there's a lot of people that are unprotected out there. But enough said about the vulnerability of Wi-Fi. One of the reasons, in a sense, that we all appreciate WarDriving is that we're trying to improve the security that exists within Wi-Fi. But again, I don't like to place the blame on the consumers who purchase the equipment which accesses it, or the consumers who have the equipment in their offices. I think that something is up to the responsibility should be in part with those who design the operating systems and those who design the hardware. They want to make it so easy to use, they make the lack of security a default rather than security a default. There are different cards to use for Wi-Fi for different purposes. Internal Wi-Fi cards. People come up to me, one of the most common emails we get is, I bought a new Dell 8600, it has great internal Wi-Fi, what do I need to hook up your antenna to it? And I say, it's not going to help you at all. These type of laptops, their Wi-Fi is not upgradable unless you want to open up the screen, solder in a connector, that's going to void your warranty, and I don't want to sell the parts for it because I don't want to get involved in the problems. So I suggest to them, what you need generally is an external Wi-Fi card that you plug in, which has an external connector, which allows you to hook up a variety of antennas. They're more power hungry than the internal card. They are going to draw power, but most people's batteries are in pretty good shape these days. Not all Wi-Fi, external Wi-Fi cards, PCMCIA or card bus, that have external antenna connectors are created equal. They run the full gamut. But there is no one Wi-Fi card which is the best. Some people prefer, of the 2 chipsets that are most commonly used are the ones based on the Hermes or the Orinoco Classic Gold, and the other one is the ones based on the Prism chipset. Again, they're both different cards. The Orinoco Gold Classic was manufactured by Orinoco. It was related to when it was part of Lucent. And when it was made, It was not only manufactured for Lucent as an Orinoco card, it was manufactured under private label for Enterasys, 2Wire, Dell True Mobile, Compaq, Toshiba. At one point, just about every Wi-Fi card you picked up was really an Orinoco. And it was a very nice design. Proxim bought the hardware licenses from Orinoco, and a company called Ageri bought the software licenses. So when you use a gold classic card these days, most of the time you're ending up putting a card in. If it's a new one, it's manufactured by Proxim, and the software still comes from Ageri. So people often ask me when they get a card, here's a real Orinoco. Is there any difference between this and the Compaq? There are about 2 bytes of difference. But from a performance basis, there is no difference. And they'll both run the same drivers. The Prism 2-based cards come in a variety of packages. Many Linux users prefer it. In particular, there's a Cisco version, which is a 100 milliwatt card. The Orinoco cards are only running at about 35 milliwatts. There's also an SMC version, which is at 200 milliwatts, and I think they've now come out with a 300 milliwatt version. So if you want power, the Prism is a good card to go to. But if you try pumping out 200 milliwatts on a continuous basis, you'll certainly drain your batteries quite quickly. One of the important issues when working with a card and you want to do serious WarDriving, and serious WarDriving would involve accepting some packets and examining their contents. This is what we would call promiscuous mode. Promiscuous mode is not as naughty as it sounds. It relates to networking, where you have a Wi-Fi card which is able to recognize and accept all the network traffic which comes along passively. So it's somewhat stealthy, and it's just sitting there and listening. And generally, you not only need a promiscuous mode, a card that will do it, you also need a driver that will allow you to do it. I put it this way. If you want to listen to the music of Wi-Fi, and you want to look at the notes that are being played, you need to become promiscuous. One of the important factors in terms of choosing a card is receive sensitivity. Receive sensitivity indicates how faint an RF signal is that can be successfully be received by your card. The lower power level that a card can receive, the better the receive sensitivity. In Wi-Fi equipment, receive sensitivity is generally stated as a function of network speed. It will generally tell you at what speed your sensitivity is. For any given receiver, the higher the data rate, the less sensitive will be the receiver, because the more power that is required to support that higher data rate. So people often ask me, I'm at a distance, it's dropping down, to 2 megabits. Yes, that's what's going to happen. That's why you put an antenna in, to increase the amount of signal that you're getting, even though you're not increasing the amount of receive sensitivity, so then you can boost up your speed again. Next slide. I'm not going to do too much math here. Just briefly, receive sensitivity is frequently a confusing issue for people. That is because it's expressed in decibels. It's not generally a unit that most of you are familiar with if you're not, working in RF or you're not working in acoustics. A decibel is a ratio expressed on a logarithmic exponential scale. So a 10-to-1 ratio is 10 dB, a 2-to-1 ratio is 3, and a 1-to-1 ratio is 0 dB. While the ratios of less than 1-to-1 are expressed as negative numbers. For example, a 1-to-2 ratio equals minus 3 dB. Received sensitivity, when you look at a card and the specifications, is expressed using a version of decibel employed in measurements of radio power, the dBm scale. 0 dBm equals 1 milliwatt. That's what I have on the scale. A power of 100 milliwatts equals 20 dBm, and 1,000 milliwatts equals 30 dBm. Power levels below 1 milliwatt are expressed as a negative number. That's just what happens when you're looking at something logarithmically. But when you need to compare the received sensitivity, for example, 0.01 milliwatts would be minus 20 dBm. And so when taking a look at it, what you really have to look at is the absolute value. What I mean by that is a signal of minus 98 dBm, okay, sensitivity is much better than the sensitivity at minus 95 dBm. Let's take a look at antennas for a moment. The simplest antenna, and what I'm going to tell you, if any of you came to the booth in the vendor area this week, again, everybody wants the biggest antenna. It's an American tradition. Bigger is always better. In WarDriving, bigger is not always better. And many of you I encourage to buy a lower gain antenna. Why? The radiation pattern of a theoretically perfect omnidirectional antenna is a sphere. That's called an isotropic antenna. However, that only exists in theory. A real antenna cannot have an isotropic, a perfect radiation pattern. The field propagates in a direction perpendicular to the radiating wire. So for a vertical antenna, the field isn't going to propagate up and down as much as it is sideways. That means that a 5 dB antenna is going to go to a certain range, but it will also go up, let's say, to the 15th or the 20th floor if you're in an urban area. If you suddenly go up to a 7 dB or an 8 dB gain antenna, you will get the additional range this way, but you will suddenly maybe not be able to retrieve a signal above the 10th floor or the 8th floor. So that's why if you're in an urban area, bigger is not always better. Directional antennas. The two I'm going to talk about are the Cantenna and the Yagi. Okay. The antenna we're looking at here on the top is a Yagi. Okay? Using a variety of elements that collect, reflect, or radiate the signal, antennas can be constructed so the transmission and reception isn't always equal in all directions. The definition of what a directional antenna is. The first antenna we're going to consider here is the top one. It's called a Yagi-Uda antenna. It's an antenna in which the gain of a single dipole element is enhanced by putting a reflector behind it, and then directional elements in front of it, so that you can take a signal and push it forward, have a gain from all the reflected power, and keep it directed on a narrow path. This antenna was invented in 1926 by H. Yagi and S. Uda. Uda's name dropped out along the way, but from what I heard from someone, he's the one who got the original patents. But a Yagi-Uda antenna is a longtime favorite. Any of you are ham radio enthusiasts? Any of you who remember what an old TV antenna looks like? Anybody ever see a TV antenna? The days before cable? Right. Those were Yagis, okay? And they were very directional, and that's why you frequently put a rotator on them to rotate it in the direction of the signal. The next antenna we're going to show you is a Cantenna. This is the original Heathkit Cantenna. This is not an antenna. I only show this to you because some people ask me, how did it get the name Cantenna? In the 70s and 80s, this is a product which is basically a 1-gallon paint can that was filled with oil. It was used to test radio transmitters. It would dissipate the power up to 1,000 watts. So you put an antenna, a transmitter on this, and you dissipated the power so that you wouldn't blow out a transmitter if you didn't have an antenna on it. That name came along, and what happened was in about 2001, Andy Clapp presented a novel design for a very simple antenna based on a Pringles can. Many of you have heard of it. The Pringles antenna showed a great potential for a simple, low-cost, less than $10, high-gain directional Wi-Fi antenna. At this point, the other high-gain Wi-Fi antennas that were anywhere near it were several $100s a piece. I don't exactly know who to credit, but along the way, someone simplified the design and came up with what we have for a current tin can waveguide antenna, or cantenna. Since it was much easier to build, the cantenna became very popular. This is an example of a commercial cantenna. Here's what a cantenna looks like inside. Essentially, a cantenna is constructed out of a can that can range from about 3 to 5 inches. You can go lower, you can go higher, but if you want reasonable gain, stay within that range in diameter. The most popular one uses a total can length of approximately 12 inches, which on a 3.5 inch cantenna results in a gain of about 12 dB and a beam width of roughly 30 degrees. You can build a cantenna yourself, and that's the whole basis for this talk. There are professionally manufactured cantennas. We sell them. There are plenty of them available on eBay and online. But you can very simply build your own cantenna, and that's how I started off in this sport, so I want to share that information with you. The tin can waveguide antenna basically acts as a collector, and the closed end on the back here acts as a reflector. What happens is that the 2400 megahertz signal that's coming in is reflected off the back, and it intersects with the waveforms that are coming in. As these incoming signals and these reflecting signals meet, there are certain points where there are troughs, and there are certain points where you have a maximum signal. It happens, the trick is that if you place the collector at about a 1/4 wavelength position from the rear of the can, you're on one of the tops. You get the maximum signal collection. At the very closed end of it, you get a zero signal. Anywhere along in the middle, you're going to get a different signal. The optimal position is about 1/4 wavelength along the way. Next. I'm going to diverge momentarily off the cantenna because you can't really use a cantenna very well without a pigtail, and I want to explain a little bit about pigtails briefly. Firstly, you don't need a pigtail to use a cantenna. Simply by having a cantenna in proximity to a Wi-Fi card, since it's tuned at the same frequency, there's a certain amount of signal strength that will radiate over, and you will get an increase. But it's minimal, and going through the air, you lose a lot of that signal. So although you don't need a cable to connect the two, I strongly recommend it. What's a pigtail? What's a cable? An extension cable is simply a cable which has two of the same connectors, one at each end. A pigtail is one which has two different connectors. That's the only distinction. The nomenclature isn't that firm, but that's at least how most of us use it. Why are there so many varieties of connectors? We've shown 3 up here. 1, not all connectors are designed to operate efficiently at microwave frequencies. 2.4 gigahertz, which is Wi-Fi, is microwave. It's the same frequency approximately that your microwave oven operates on, except that's running at 4, 5, 800 watts, and we're talking here about milliwatts. Manufacturers want you to purchase their accessories for their product, so they use a custom connector, and you're forced to use their antennas with their Wi-Fi devices. But it also originated with the FCC. Part 15 of the FCC code says that the frequency we're working in, at around 2400 megahertz, is in public domain. However, you're limited to an effective radiated power of about 4 watts. The way the FCC managed to limit manufacturers was to say that if you had a D-Link antenna and you had a D-Link router, D-Link had to go and submit approval for the antenna and the router in combination together. And until last year, 2004, summer of 2004, the FCC came out with a new ruling which said you could mix and match. Technically, before that summer ruling, if you took a cantenna and put it on a Linksys router, you were doing something not permitted by FCC Rule 15, because you might have increased the power above the limit that they wanted to. To comply with the FCC, each manufacturer came up with somewhat of a custom connector and got it approved by the FCC. Some took the popular SMA connector and they reversed the ground and the signal, and you came up with an RP, which is a reverse polarity SMA cable. Others came up with a custom connector called the MC, which is what Orinoco uses. It's somewhat of a fragile connector, but again, we didn't design it. They came up with it, so it was customized for them. Samsung took the SMA connector and reversed the threads on the connector, and you have something called an RT SMA. So, one thing is, when you get to the point at which you're looking for pigtails, be very careful which pigtail you're looking for. An SMA is not an RP SMA, it's not an RT SMA. Look carefully, talk to people you know, go up online, there's some tables for each one of the types of equipment so that you can find out which type of cable you're going to use. The other important thing to keep in mind with connectors is, people say to me, I'm a CB enthusiast. I have a PL259 connector. It looks about like an N connector. It does. It, however, was never made to operate at microwave frequencies, so you're going to see a lot of loss. Choose a connector, preferably an N, that is efficient at microwave frequencies. Cables. What makes a good cable? People are always calling me up and saying, I want a really, really low-loss cable. A really, really low-loss cable is about 3/4 of an inch in diameter. It takes 2 people to carry it down the street, okay? But yes, it works. The thicker the central conductor on a coax cable, the stronger the shield. There's almost this direct correlation. The lower the loss of the signal along the cable. However, the thicker the cable, the less flexible. The cables you're generally going to run into are an LMR 400, and that's about 3/4 of an inch, sometimes almost an inch thick. It's very heavy, it's very bulky, but if I'm running a 50-foot span up to the roof, and I know I'm only going to lose 6 dB over 100 feet, here's a piece of LMR 400, okay? This is not the type of thing you want to plug into your little laptop, okay? This is what we call equivalent to about an LMR 200 cable. It's a lot lighter weight, it's a lot more flexible. If you're going to do a run of 20 feet or less, this is a great cable to use. They call it LMR 240, they call it LMR 200, they call it low loss 200. Great cable to work with. This is an LMR 100 cable. Very thin. On the other hand, if I'm trying to connect this into a card that I plugged into my laptop, I certainly couldn't plug in that LMR 400 into it. One, there's no place to put the connector. Two, the weight of it would break the connector. So we use pigtails to connect from one size of a connector up to another. But just be careful, in a sense, when you're looking for a cable, you have to decide how long it's going to be. Now that you know a little bit about cables and you know a little bit about connectors, the next step is you want to build a tin can waveguide antenna. That's what you all came to hear. What are the parts and tools you're going to need? You're going to need a tin can. You're going to need an N connector. You could use another microwave connector. I'm going to use my example using an N connector. The example stays the same. You're going to need a drill or a device to make a hole in the can. You're going to need a short piece of wire. You only need about 1 1/4 inches, but I would say start off with about 6 inches so you can make a few mistakes. You're going to need a soldering iron and solder. A little flux doesn't hurt. My partner here, King Tuna, makes them. He says if you've soldered, put a little flux on it, and it's going to make life a lot easier. And most importantly, you're going to need a ruler. Don't do it by line of sight. Sorry, by sight. Choosing a can. You can choose many different types of cans.
This helps in the build process.
Yes. Yes. King Tuna says I build better canned tunas when I've had a shot of Jack. But we've used coffee cans work. You can eat beans. Baked beans cans work great. Particularly anybody here from England? The baked bean cans are a lot wider there, and they're much better for a cantenna. Or you can use or drink scotch at holiday time, and it comes in a nice little metal commemorative can, which happens to be almost perfect for a great cantenna. Stoli also provides them. You can download plans for many of the cantennas. We're going to distribute one plan here off of the internet. Some of them will have very exact measurements of how to build it. Relax, you don't have to be that exact. You can be within 10% and still make a good cantenna. There are some dimensions which are important. You start off by having an end connector. This is an end connector. You're going to take this end connector. It has a female end on one end, and it'll have a little stub on the other side. You're going to be soldering a piece of copper wire to that. We have, in my business, we happen to use a little brass tube that we have pre-soldered. You can use a brass tube, you can use copper, you can use a copper piece of wire. They'll all work about the same. You need 1.21 inches for a radiator to be effective. Why? Let's go to the next slide, please. Okay. Now, they've just told me I only have 10 minutes because we started a little late, so I'm going to try to go briefly. The first thing to determine is based on the width of the can, the diameter of the can that you have will determine what the length is for a wavelength. You need to position the collector 1/4 wavelength from the end. That's the optimal point. That is the distance that you have to be careful on. Anywhere a little further, a little less, the cantenna will still work, but you'll get lower gain. The other important measurement is what we call L/4 here, which is the length of the radiator, which is going to collect the signal. That should be as close to 1.21 inches as you can. Using a ruler, to make a cantenna, here's an example of one that my partner King Tuna made. It took him about 15 minutes this afternoon. This is made from a 13-inch coffee can, 13-ounce coffee can. It's not necessarily the optimal can to do it, but it shows you can do it with any can. At CVS he bought it. You take this can. We've got some plans. You can go up and there's some calculators that will give you that are on the internet, which based on the diameter of the can will tell you the distance out from here that is 1/4 wavelength. Cut a hole. In this case, we just used a screwdriver and a mallet to cut a hole that's about 5/8 inches around. You take the radiator that you've constructed, which looks like an end connector, with a 1.21 inch piece of copper wire or brass rod, insert it, screw it down. You don't need for it to be a round connector. If you've got a square connector, you can use that. You can screw it in place. You can glue it in place. The other dimensions are not going to be that important. For an optimal cantenna, you want this length to be approximately at least 3/4 of a wavelength. For this particular can, which is 4 inches across, 3/4 of a wavelength works out to be 5.15 inches. This happens to be 5.25 inches. The 13-ounce coffee can just happens to work well. Put it in, screw it down. That's all there is to building a cantenna. Essentially, the only part that you're going to have a problem finding is the end connector. You can get them from radio supply houses. We may even have a few left at our booth. There are plenty of places to buy them on the internet. That, a 1.21 inch radiator, and a good tin can. Take that. This particular one is 4 inches, 100 millimeters. 4 inches across. I could go over the math, but basically the distance that you're going to measure from here to there is going to change based on the diameter of the can. If you want, you put a pigtail on. You can then connect it up to your card. A simple cantenna like this, which took about 20 minutes to build, will give you about somewhere between 8 to 10 dB gain. We haven't fully measured this. If you're a lot more careful about the calculations, if you're a lot more careful about the length of the can, you could probably get 12 to 14 dB gain. If we make this shorter, we will get less gain, but then again we'll get a wider signal coming out of it. Some people have made them about 4 inches or so, and they get about a 50-degree signal breath. If you make it about 12 inches long, you're going to drop down to about a 25 or a 30-degree signal breath. So decide what you're using your antenna for. We find it very useful to go to Home Depot, pick up a little tripod thread, a 1/4 by 20 inch, 1/4 by 20 threaded bolt. Put it on there, screw it in, and now you don't have to take your coffee cup and try to measure it and get it off and left to focus it. You can put it on any camera tripod. It's really very simple to build a antenna. Again, the 2 calculations necessary. The length of this is 1.21, and go and find either use the plans that we've got for working with a simple coffee can, or go on the web. We've got a website where you can go to a calculator and measure this out so it's 1/4 wavelength. Any questions? The optimal radiator is a trapezoid. It's actually a cone, but it's pretty hard to make a cone like that. So by making a rod, we end up trying to get in the middle channel. See me afterwards. What you want is a trapezoid with, I think it's 6 millimeters at the bottom and 1 millimeter at the top. Again, 1.21 across. That's optimal. Yes? No. We tried it with copper. We tried it with bronze. We even tried it with aluminum. They all work well. We didn't see a significant difference. Yes? Thank you very much.